Can you see my screen?
Yes,
Yes,
sir.
sir.
Okay, all right, thank you. Okay, so let me recall what we did in the last class. In the last class, we proved the spectral theorem for normal matrices. So we defined normal matrices first, and then we proved spectral theorem for complex normal matrices. So what it says? It says that if we have a normal matrix, then it is equivalent to saying that the matrix is unitarily diagonalizable, which is also equivalent to saying that there is an orthonormal set of n eigenvectors. And there was one more condition. So in today's lecture, we will first so a real version of spectral theorem for normal matrices. That means the spectral theorem for real normal matrices. And then as a corollary of that, we can we can write statements for certain matrices like symmetric, skew symmetric, or matrices that have a particular structure. We can write them also this kind of spectral theorem. Okay, so let us recall how did we prove that. So what we did in the spectral theorem for complex normal matrices. So we saw that A is normal. So if suppose A is n cross n matrix over C, then this is normal. This is normal means A star equal to A star. This implies that there exists U unitary such that U star AU is diagonal, and converse is also true. Okay, so if A is unitarily diagonalizable, then converse is very straightforward to check. So just to check that this property is satisfied, and if uh, for conversely, suppose A is normal, then in order to prove that that A is unitarily diagonalizable, how did we do that? We use Schur's theorem for complex matrices. So that means if I recall what we did, we first applied Schur's theorem on A. So A normal is given. So by Schur's theorem, there exists unitary U such that U star AU is some upper triangular matrix T. But then since A is normal, so that means A star equal to A star. This implies that T is normal, and T normal means this condition is satisfied. But this condition implies that all the off diagonal entries of T are 0. So T is actually diagonal. So an upper triangular matrix is normal implies that it is a diagonal matrix. And this is how whatever transformation we have for the from the Schur's theorem, that transformation works, and that gives us a diagonal matrix. Okay, so now if I want to state a similar result for real normal matrices, so before I write the proper precise statement, so I want to just get some idea from you that how can we proceed for this, and what would be the statement for what can we expect. So in general, if suppose if I take, so let me give you one example. So this is what I just recalled from previous lecture. So I'll remove this now. So we can start today's lecture with this example, that if suppose we have let's say if I take this matrix A, let's say 1 minus 1 1 1. Okay, now this matrix, you can verify that this matrix is a normal matrix. Okay, that means A star A is equal to A star. So this A is normal. So by spectral theorem of normal matrices, so if you assume that this matrix A over C, then you can say that there exists U. That means this matrix A is unitarily diagonalizable. That means there exists U such that U star AU is diagonal, where the diagonal entries are nothing but the eigenvalues of this matrix A. So this matrix has two eigenvalues, 1 plus iota, 1 minus iota, two complex eigenvalues. So definitely we cannot say, now if suppose that same matrix, if you consider over, so if I consider A over C, then you can do that. Now if you consider the same matrix A over R, then can you say that there exists a real orthogonal matrix such that U transpose AU is diagonal? What is your answer? So can we say, so this is the question mark, that there exists U is real orthogonal such that U transpose AU is diagonal?
No, sir.
No, why?
Because, sir, if U is real and also A is real, then the product of these matrices cannot be complex.
Yeah. So if it is equal to a diagonal matrix, then this implies that this diagonal matrix is real and the diagonal entries are the eigenvalues, but this matrix doesn't have any real eigenvalue. So clearly, if you consider this matrix A over R, then you cannot say that there exists a real orthogonal matrix such that U transpose AU is diagonal. So the answer to this is that there does not exist U. In general, there does not exist U. So in this case, it is n equal to 2. Sorry, so here this n is equal to 2. So there does not exist U such that U transpose AU. So U is real orthogonal such that U transpose A is diagonal. There cannot exist. Okay. So then the next question is, what is the best form? So in general, we cannot say, we already seen one example. So we cannot say that if we have a real normal matrix, then there exists a real orthogonal matrix U such that U transpose A is diagonal. So we cannot say that in general. Then the next question is, what is the best form a real normal matrix can have under real orthogonal similarity transformations? You understand what I'm asking? So I just want to answer the question, the same question for real normal matrices. What we had for complex normal matrices, can we have similar thing for real normal matrices also? So the question is here, what is the best form uh, real normal matrix can have under real orthogonal equivalence or similarity or equivalence? So this is the question. Now what would be your answer? Can you guess something that, okay, it cannot be diagonal, but then it is probably this one? If not
Block
diagonal, then
diagonal with size of 1 or 2 blocks.
right. And what are these blocks on the diagonal represents? Any idea? So you are saying that,
Eigenvalue.
yeah, eigenvalues. So what he's saying, so let me explain. So he's saying that if A is real orthogonal such that A transpose A is equal to A transpose, that means not sorry real orthogonal, it's a real normal. So if it is a normal matrix, then there exists U or real orthogonal such that U transpose AU is not diagonal, but it is of the form block diagonal, where these AIs, these blocks on the diagonal, they are either 1 cross 1 or 2 cross 2. If they are 1 cross 1, then they are the eigenvalues. They are actually the real eigenvalues. And if they are 2 cross 2, then they are the block corresponding to the complex eigenvalue. And you know, for a real matrix, complex eigenvalue appear or occur in pairs. Okay, so they are if it is a 2 cross 2 block, then it is corresponds to a pair of complex conjugate eigenvalues, right? In particular, these pairs should have some form, because if it is if the eigenvalue, if ai, if it is a 2 cross 2 block, and the eigenvalues of this 2 cross 2 block are just the complex conjugate of each other, then this block should have this form, like this kind of thing, alpha I beta I minus beta I alpha I, this kind of form. Okay, so in fact you can write this as a statement, and this will be your spectral theorem for real normal matrices. And the proof is exactly similar to what we uh, so it follows using the similar ideas as we use for spectral theorem for complex normal matrices. That means we started by applying a complex Schur's theorem there. Here we will apply a real Schur's lemma, and then we will see what happens. Okay, so I won't give you the complete proof. I will just give you the idea, but then it is simple computation. So if the idea is clear, then proof you can write yourself also. So let me first write a precise statement for this spectral theorem for real normal matrices. Okay, this result is interesting and also important, because you will see that using this you can say you can state this kind of result for especially when A is of particular structure, like A is real symmetric or A is real skew symmetric, because these are like real normal matrices. Or if you take some other real normal matrix with a particular structure, then you will see that you will get a like nice diagonal form. If not diagonal, then it would be a block diagonal in a nice, like with a nice structure. You will see that. So we will see that those corollaries also. But let us first write the spectral theorem for real normal matrices. So what it says that if we have a real matrix of size n cross n, then A is normal. That means A transpose A equal to A transpose if and only if and only if there exists a Q of same size over R, which is real orthogonal, such that Q transpose AQ is block diagonal, where at the diagonal we have this block A1, A2, and so on up to AK for K greater than equal to 1, less than equal to n, where this AJ, this diagonal block AJ is either a real, for each J, this AJ is either a real 1 cross 1 matrix, that means a real number corresponding to a real eigenvalue of A, or is a real 2 cross 2 matrix corresponds to the complex conjugate eigenvalues of A of the form. So if it is 2 cross 2, then the AJ would be of the form alpha j beta j minus beta j alpha j for some alpha j beta j in R for each j. So I can write here where for each j, AJ is either a real 1 cross 1 matrix corresponds to a real eigenvalue of A, or a real 2 cross 2 matrix corresponds to a complex conjugate eigenpair, eigenvalues of A. So this is an if and only if result we need to prove. So I'll just give you idea how to prove this, and then you can explore or you can complete the proof. So it is if and only if, so you have to prove both ways. One way is very straightforward. So you can easily verify the only if direction. That means if you assume that there exists a matrix Q, real orthogonal, such that Q transpose AQ is of this form, then you can easily verify that this matrix A is real normal. So this A matrix is normal. So this you can easily verify. So if you assume that let's say this matrix here is, let's say, some D matrix, then A would be QD Q transpose, and then you can easily verify that A transpose A is equal to A transpose. So this follows by direct calculation. So this you can verify. Okay. Now look at the if direction. So suppose that we have a matrix A which is normal, and now we have to prove that there exists a real orthogonal matrix Q such that Q transpose AQ is in this block diagonal form. Okay. Now can you give me a start for this for this direction? So how can we start the proof for this direction? Any idea? So you already know that if we have a real n cross n matrix, then because of real Schur's lemma, there exists a Q real orthogonal such that Q transpose AQ is block upper triangular, right? So then we will write that like we did in the complex spectral theorem case, in the case of spectral theorem for complex normal matrices. So there we use complex version of Schur's lemma. Here we will use real version of Schur's lemma. And then since it is a real matrix, there exists a Q such that Q transpose AQ is block upper triangular, where the diagonal blocks are either 1 cross 1 or 2 cross 2. Then using the fact that A is normal, we will try to show that these off diagonal entries they are 0, only the diagonal blocks remain there. Not only that, all the 2 cross 2 diagonal blocks, they should have a particular structure. That means the 2 cross 2 blocks have this kind of structure here. Okay, so it follows because of that. So let me just give you some hints. Now, by real Schur's lemma, now you tell me why we can always do that. By real Schur's lemma, I know that there would be a Q such that Q trans. So by real Schur's lemma, let me write, there exists Q such that Q transpose AQ is equal to a block diagonal, right? Here, where the block like this kind of thing. So I'm just I'll erase this thing, but just to explain. So we know that this real Schur's lemma, there exists Q. Q is real orthogonal such that Q transpose AQ is block upper triangular. So these AKK, these AJJ blocks here, they are either 1 cross 1, 1 cross 1, or 2 cross 2 real matrices. If 1 cross 1, then they are correspond to real matrices, and they are corresponds to complex conjugate eigenvalues. Corresponds to complex conjugate eigenvalues of A. Right? Now, in particular, in this, if you recall the real Schur's lemma statement, it also says that these blocks you can arrange in any order. These diagonal blocks here, these blocks you can arrange in any order. So you can arrange at the beginning, you can arrange them in a particular order, and then you can always find a Q such that Q transpose AQ gives you the diagonal blocks in that prescribed order. Therefore, without loss of generality, you can assume that the 1 cross 1 blocks, that means corresponding to real eigenvalues, they appear first, and the 2 cross 2 blocks are at the bottom on the diagonal. Okay, so you can assume that. So what I'm saying is the following, that you can assume that your matrix, there exists a Q real orthogonal such that Q transpose AQ is of this form R. Then let's say A01 to A0K, then this A11 and so on up to AKK. This is A12, A1K, and so on. This is A22 here, and A23, and so A2K, and so on. Okay, so these are diagonal. So where this R is an upper triangular matrix, where R is upper triangular, because the R is they are corresponding to the diagonal entries of R are corresponding to 1 cross 1. So they are corresponding to real eigenvalues. So this is a real matrix of size P cross P. So this is upper triangular, and this Aij, for all Ij, they are real matrices of size 2 cross 2. I can always write it in this way, right? So if I assume that this matrix here, if I somehow show that this matrix here is actually upper triangular, or not upper triangular, is block upper triangular, not block one, sorry, is block diagonal. That means if I show that all these blocks here, they are 0, then I'm almost done. Then I can say that there exists a real orthogonal Q such that Q transpose AQ is block diagonal, where the diagonal blocks are either 1 cross 1 or 2 cross 2. The only thing remains to show that these 2 cross 2 blocks have this particular structure. Yeah. Right? So in the following, and if I show, so that means in the right hand side, if I show this, so let's say this is my matrix, let's say T. So if I somehow show that this T is diagonal, is block diagonal, or if I show that all these blocks here, they are 0, then I'm almost done. Okay, so what would be my claim? So my claim here now, in order to prove this result, my claim would be, so my claim is to show that the first thing, that this R is diagonal, right? R is diagonal. So because I want to show that all these blocks are 0, and this R right now, R is upper triangular, so I need to show that these entries are also 0 here. Then only I can say that this is just a diagonal matrix here, and these are the blocks remain and all the other blocks are 0. So then only it would be block diagonal. So I will show that first R is diagonal. Then the second, I'll show that each of these Aij block is 0 when j is greater than I. So that means all these blocks are 0 except the diagonal. All these 2 by 2 blocks are 0. Okay, and then third thing, I will show that each of these AJJ blocks, that means these blocks, they are of the form alpha j beta j minus beta j alpha j for some alpha j and beta j. So if I do that, then I'm done. Right? Now, how you can show this? So the first thing, so I'll just give you some idea for the first part here. Then the second part, this follows similarly, and this also you can easily verify for 2 cross 2 blocks. So first I will show that this R is diagonal. Okay. So now we can use the fact. So far we have not used the fact that A is normal. A is given to be normal here. So we have not used this fact. Now we will use it. Okay. So since A is normal, this implies that A transpose A is equal to A transpose. Now A is normal implies that T is normal. Okay. So what is T? T is this one here. So A is normal implies T is normal. Now T is normal means T transpose T is equal to T transpose. Now if you do that, if you compare the first diagonal block here in T transpose T and T transpose, can you multiply and tell me what would be the first the 1 block of T transpose T? Can you tell me that? So look at here, T is this one. If you do T transpose T, what would be the 1 block here? One block means the block corresponding to R.
R square.
R square or R transpose R?
Oh, R transpose R.
R transpose R, because R is not, you don't know whether it is symmetric or not. So right. So if you compare, so then this implies T transpose T equal to T transpose corresponding to block R in let's say here. I can give you this as a name. Let's say star. Okay. So corresponding to block R in star, what we get? So when we do T transpose T, so the 1 block in the left hand side would be, as you are saying, R transpose R. And what would be the right hand side? That means the 1 block in the right hand side, T transpose.
RR transpose.
Just RR transpose? Or there is something else also? Just look at here T. When you do T transpose, what would be the first entry? What would be the 1 block entry?
So RR transpose plus A naught A0 A transpose A0 A something like that.
Right. Exactly. So when you just multiply and look at the 1 1 entry, 1 1 block entry, then it would be RR transpose plus A01 A01 transpose plus A02 transpose and so on up to A0K A0K transpose. Okay. So let us give it some name 1 equation. Okay. Now what we are trying to show, you can see here, we want to show that R is diagonal. Okay. What we are given R is upper triangular. R is upper triangular. And we want to show that R is diagonal. So if I somehow show that R is normal, that means R transpose R is equal to RR transpose, and R is upper triangular, then this implies that all the off diagonal entries are 0. See, because of the same reasoning, if you compare both sides, you will see the off diagonal entries are 0. So if a upper triangular matrix is normal, then it implies that this matrix is diagonal. So if I just show that this R is normal, that means if I show that R transpose A equal to RR transpose, then I can say that R is diagonal because R is given to be upper triangular, and this condition implies that R is diagonal. But in order to say that R transpose R equal to RR transpose, I need to show that these terms here, they are 0. Right? Now, can you give any idea? Can you think of some idea so that we can show that these terms are 0 using some well-known uh, matrix result or some other things? We want to show that
When
these
J is
terms
greater
here.
than I, Aij is 0.
Sorry. Can you repeat? What did you say?
J is greater than I, Aij is 0.
No, this is not given. This is not given. This is, we have to show here. See, in order to prove the result, we have to prove these 3 things. Okay, and I'm trying to prove the first thing here, that R is diagonal. Then next I will show that these things are 0 for each I. Now the first thing, so these things are not given, so we cannot assume that they are 0. We have to show that they are 0. And this is what we are trying to do. First for the block, for the entries corresponding to block R. So that means first I'm trying to show that these blocks are 0. Because if these blocks are 0, then A transpose A implies, because of this, R transpose R equal to RR transpose. And since R is upper triangular, so this implies that R is diagonal. So this will be done if I just show that these blocks are 0. That means this A0I, these blocks are 0, or these terms are 0 here in this sum. So I need to show that this sum is 0. Then I can say R is diagonal. So any idea how we can do that? Okay, so if I take, let's say, trace both sides. So let me do that. Okay. Or maybe I'll just give you this idea and then you can verify yourself, because we don't have much time also. So if you simply use the trace argument, so if you take trace both sides, then it would be trace of R transpose R, and here the trace of this sum here, trace of this sum, but then trace of the sum is equal to sum of the traces. So trace of these, and so on, plus trace of this. So the left hand side is trace of R transpose R, the right hand side is trace of this, and so on, plus trace of this. Now trace of R transpose R is same as trace of RR transpose. So these two will cancel out. What will be left is a trace of 01, 01 transpose plus trace of 02, A02, A02 transpose and so on, plus trace of A0K, A0K transpose equal to 0. Now, if the trace of this is equal to 0, so from here we can say that the trace of this equal to 0, but then that argument implies that each of this term is 0. That is an exercise for you. Just think about it, why it is. So using the trace, or by taking the trace, by taking trace both sides, implies that A0J transpose equal to 0 for all j equal to 1 to k. Okay? This you verify. Why this is an exercise for you. Okay. Now, if this is the case that all these terms are 0 here, then from 1 you can say that, so from 1 you can say that R transpose R equal to RR transpose, but R is upper triangular. This implies that R is but R is upper triangular. This implies that R is diagonal. This implies R is diagonal. Okay, so R is a real P cross P diagonal matrix here. So we have shown that this R that we get from the real Schur's form, because of the normality, this R should be diagonal. So we have shown that all these, if R is diagonal means, so R is diagonal, we have shown this. Okay. All right. Now we will show that all these blocks here, they are 0. Now how to do that again? So similarly, now you can do the same thing. So what we did here, we have compared the 1 block of this. Now you compare the 2 block, then the 3 block. Okay. So all the diagonal blocks in this T transpose T and TT transpose, so the left hand side and the right hand side, you just compare the diagonal blocks. If you keep on comparing the diagonal blocks, then you will get using similar idea, using the same argument, so same trace argument, you can show that all these blocks here, they are 0. Okay, so I have removed something here. From here, Aij is 0 for all j is I. Okay, so what I'm saying is that similarly, next, equate the main diagonal 2 cross 2 block entries. If you do that, then this implies that Aij equal to 0 for all j greater than I. Okay, this also you can verify, and this is an exercise for you, why this is true. So what we have shown that if, so I'm saying that this is true, so you can verify yourself. Now if this is true, then this implies that this matrix here T is block diagonal. So the proof is over if we just show that all these blocks here, that means A11 to AKK, the diagonal blocks, they have this particular structure. So we just need to show that these AJJ blocks are of this form. Okay, and then the proof is over. So the proof is over. So the proof is over if we show that for each j, AJJ has the form has the following form. That means AJJ is of the form alpha j, beta j, minus beta j, alpha j for some alpha j, beta j in R. So we just have to show this. Okay. So since A is, again you look at here, A is given to be normal. So this implies, I have already written this. This T is a normal, and T we know that now because of our proof, T is a block diagonal because all these blocks we have shown that they are zero. So T is a block diagonal matrix which is normal. That means each of these blocks, they are normal. They are 2 cross 2 blocks, they are normal. So T transpose T equal to T transpose. This implies that these diagonal blocks here, they are also normal. So if I show that each of these blocks have this particular structure here, then the proof is over. Okay, so let us assume that this 2 cross 2 block AJJ, since it's a 2 cross 2 block, so let us assume that it is of this form ABCD. So let AJJ is of this form. It's a 2 cross 2 block, 2 cross 2 real matrix. And this is also normal. So because T is normal, so this implies that all these blocks, 2 cross 2 blocks on the diagonal, they are normal. So this implies what? This implies that AJJ transpose AJJ is equal to AJJ transpose. Now if you just multiply the left hand side, so if you just compute left hand side and right hand side, and if you compare the entries, then you will get the following. So when you compare all the entries here, then you will get this condition that B square is equal to C square and AC plus BD is equal to AB plus CD. If you just compare both sides, you will get this. Now if B square equal to C square, this implies that B is equal to plus minus C. Okay. So B is equal to plus minus C. Now if B is equal to C, now you can, for this condition here, you can consider two cases when B equal to C or B is equal to minus C. Now if B equal to C or if B equal to 0, then this cannot occur. So what I'm saying that B equal to C or B equal to 0, this is not B equal to C and B equal to 0. These cases are not possible. So the only possibility is that B equal to minus C. Now can you tell me is not possible? Not possible. Why these two things are not possible? So what happens if, let's say, if B equal to C? What happens for any J? If AJJ is in this form, then B equal to C and B equal to 0. These cases are excluded. This cannot happen. Why? What happens if B is equal to C in this?
B equal to C will imply that AJJ is diagonal. Sorry, B equal to 0.
B equal to 0 and B equal to C implies that AJJ is diagonal, which is not true, which cannot happen. Why?
Because we are taking only 2 cross 2 blocks in the form of AJJ.
Right, 2 cross 2 block corresponding to the complex conjugate eigenvalue. If it is a diagonal matrix, then that means AJJ have two real eigenvalues, but then the eigenvalues of A here. we have already taken all the real eigenvalues are here in R. These are corresponding to the complex eigenvalues. So this cannot happen. So the only possibility, and similarly for if B equal to C, then also this is the case, because when B equal to C, then this is a symmetric matrix, real symmetric matrix, and we know that real symmetric matrix, that means it is a Hermitian matrix, it has only real eigenvalues. So again, if it has real eigenvalues, then they should go in R. So these AJJ are corresponding to the complex eigenvalue of A. So this cannot happen again. So these two possibilities cannot happen. So only thing remains is B equal to minus C. Now if B equal to minus C, then from this expression here, what we have 2B A minus B equal to 0. And we have already seen that B cannot be 0. So this implies that A is equal to D. But that means AJJ is of the form A B minus B for each J, and we are done. Okay. So we have proved the real version of spectral theorem for normal matrices, or you can say the spectral theorem for real normal matrices. It says that if you have a real normal matrix, then it can always be real orthogonalized to a block diagonal matrix, or you can say that it is real orthogonally similar to a block diagonal matrix, where at the diagonal we have this kind of blocks which are either 1 cross 1 or 2 cross 2. If it is of 2 cross 2, then it has this structure. That means this 2 cross 2 block has two complex conjugate eigenvalues. All right, so this is fine. Now using this, you can state spectral theorem for several other matrices. For example, so you keep in mind this result. So you keep in mind this spectral theorem for real normal matrices, and tell me a statement for the following matrices. Okay, so we can write it as a corollaries of this. So what I'm saying is the following. So let us suppose that let A be a real n cross n matrix, just a real matrix. Then using the above result, can you say, so if suppose A is, so let's say A is equal to A transpose. So A is a real matrix which is symmetric. Okay. Now, can you say that A is symmetric if and only if something like we had here from the above result? So A is symmetric means clearly A is normal. So these are particular case of normal matrices. Now I'm saying that what would be the statement of this result, the previous result we just proved, for this kind of matrices, for real symmetric matrices. So what can you say?
So Q transpose AQ will be diagonal.
Yeah, so what would be the statement? Can you just state the precise statement that A is equal to A transpose if and only if?
There will be a real orthogonal matrix Q such that Q transpose AQ will be diagonal.
Why this is?
Because all the eigenvalues of symmetric matrix is real.
Are real, right? Exactly. Because of that, and if you just apply the previous result on this A equal to A transpose, then since A is a real normal matrix, so if you just apply the previous result, then you can say that there exists Q such that Q transpose AQ is in this form. where these block diagonals are either 1 cross 1 or 2 cross 2. But since A has all real eigenvalues, so there would be no 2 cross 2 block. So that means this D matrix here would be diagonal. So what you can say here is the following, that if A is a real matrix, then A is equal to A transpose if and only if there exists Q real orthogonal such that Q transpose AQ is equal to lambda 1 to lambda n. That means diagonal matrix where with lambda I is in R for all I. Okay, fine. Now this is immediate. Now can you state a similar result for this also when A is equal to minus A transpose? That means it's a real skew symmetric matrix. So I want a similar statement for this also. So again, can you say similar thing for this also? Let us look at again. Yes. So just apply the fact that A is equal to minus A transpose. Then what can we say?
Sir, that diagonal block will be 0.
Diagonal block would be 0. Okay, that means the why this would be?
Because for skew symmetric matrices, the eigenvalues are either 0 or imaginary.
Yeah, so all the real eigenvalues would be 0. That is fine. And what can you say about the other blocks? So you are saying that the block corresponding to 1 cross 1 entries, they are 0. So what about the 2 cross 2 blocks?
2 cross 2 blocks will be normal blocks.
Normal blocks, that is fine, but what would be the form? Can you say even something more? So A is equal to A minus A transpose. That means A is skew symmetric, means all the blocks here, they are also skew symmetric. So if this matrix is skew symmetric, what can you say about the alpha j and beta j? This A, the 2 cross matrix, skew symmetric. What can you say about the alpha j and beta j?
Alpha j will be 0.
Right, alpha j would be 0. So what would be the statement here? Now you can write it using this result. That A is skew symmetric if and only if there exists Q, again real orthogonal, such that Q transpose AQ is of the following form. It will have either 0 1 cross 1 block or these A1 to AK, these blocks, where this AJ for EJ, AJ is of size 2 cross 2 over R of the form of the following form. That means AJ is of the form 0 0 beta j minus beta j for EJ. So this is also fine. Now suppose you have a real orthogonal matrix. That means A transpose equal to I. Okay. Now what can you say? Suppose A is of this form. So if A transpose equal to identity, then what can you say about the real eigenvalues? So you just have to look at the real and complex eigenvalues of these matrices. So in the case of symmetric, it has only real, so no complex, so no 2 cross 2 block. In the case of skew symmetric, it has either 0 eigenvalue or it will have purely imaginary eigenvalues, and therefore the diagonal entries are 0, or the 2 cross 2 blocks of this form. Now we have an orthogonal matrix. Now suppose that A satisfies these. A transpose is equal to identity. Then what are the possible eigenvalues of A? So what are the possible eigenvalues of A?
So non-zero.
Eigenvalues are non-zero, that is fine. But here we are more concerned about real and complex eigenvalues. In order to specify the diagonal blocks in the real spectral theorem.
Sir, of unit modulus.
Of unit modulus. So then, if they are real eigenvalues, then what are the possibility?
Plus 1 and minus 1.
Plus and minus 1. So the real possibility, the real eigenvalues possibilities are either 1 or minus 1. So the diagonal entries would be either 1 or minus 1. And what about the 2 cross 2 blocks?
0 and minus 1, 0 will be the blocks.
Yeah, so basically your 2 cross 2 blocks can be, so there are any 2 cross 2 blocks that have eigenvalues of modulus 1. So that means they are actually a 2 cross 2 rotation kind of thing. Okay, so you can verify this, why this is true. So what I'm writing here, if and only if there exists Q the same way, real orthogonal, such that Q transpose AQ is equal to lambda 1 to lambda P and A1 to AK, where these lambda J's are either plus 1 or minus 1 for each J, and AJ is a 2 cross 2 matrix corresponding to the complex eigenvalues, but the eigenvalues are only of unit modulus. So this AJ would have this form of the following form, that cos theta j sin theta j minus sin theta j cos theta j for some theta j in R. Okay. So this is not difficult to see why this is true, because if A is orthogonal, that means A transpose equal to I, then all these blocks also satisfy the same thing. That means AI transpose is equal to 2 cross 2 identity. So if you just compare the diagonal entries, so we know that these AJ are of this form, right? Alpha J minus beta J and alpha J. In general, they are of this form. But since AJ transpose equal to identity, if you just compare the diagonal entries, then you will see that the diagonal entries of the form alpha J square plus beta J square equal to 1. So diagonal entries, if you compare, then it will give you this condition for each J. You will get this. But since alpha J square plus beta J square equal to 1, so you can say that there exists, you can write it in terms of cos and sine. So there exists theta j in R, such that alpha j is cos theta j and beta j is equal to sine theta j. And then you just substitute it here, and therefore you have this one. Okay, so I'll erase this. So now you can see that if you have a particular normal matrix, then you can see what would be the structure of, what would be the version of real spectral theorem for that. All right. Similarly, depending on your matrix, you can look at the eigenvalues and then you can state the corresponding result. All right. So now we have covered spectral theorem also. So if you recall from the previous lecture, now the next thing would be singular value decomposition and then Jordan canonical form. in this section, in this matrix factorization. But before going to SVD, I need these positive semi-definite definite matrices. Okay, so I'll take one lecture on this, maybe the remaining of today's lecture. So that means the next 30 minutes, and possibly the half an hour in the next lecture to cover this positive definite semi-definite matrix. This is not difficult to see. You might have already learned what are these matrices. So I'll quickly go through it, and then I need this in order to define SVT. Okay. So let me. So is there any question so far? If not, then I will define positive definite matrices. By the way, let me recall. So let me see how many of you are there in the lecture. Okay. So as I mentioned in the last class, there would be a quiz in the next week on Tuesday at 4 o'clock. And this quiz will be via Gradescope. That means you might have already received one email that you have been registered in Gradescope for this course, MTL 745. So I will upload the question paper there, and then when the quiz starts, that means at the right time, it will be visible to you. So you can download the question paper, then you can write your answers in plain paper, and then you have to upload your answers, your solution with details on the Gradescope itself. Okay, so there is an option there. So if you are not familiar with the Gradescope, you please be familiar how to do that. And during the exam, since I am announcing it well in advance, I will not entertain any such thing like we are not familiar, or there is some network issue, or anything like that. So there would be no re-quiz. Or if you miss the quiz, that means you have missed 10 marks. So there won't be any re-quiz. So please make sure that you have a good connectivity. Please make sure that you are familiar with the Gradescope. So you just be with it, and you have to upload your answers within the given time. So I'll send more details regarding the quiz by today evening, in the late evening. And then accordingly you can prepare yourself. And the syllabus is everything we have covered so far, I mean, till today's lecture. Yeah. Any question? Yes.
I guess the quiz timings was 6 p.m., not 4 p.m.
6 p.m. Had we decided about 6 p.m.?
Yes,
Okay.
actually we have one class from 3:30 to 5. So.
Okay. On Tuesday.
Yes, sir.
Okay. Okay. So I thought that it was 4 o'clock. Okay. Anyway, so we can have it at 6 o'clock then.
Thank you.
So Tuesday at 6 o'clock. Yeah, no problem. All right. So let us define positive definite matrices. So if suppose we are given an n cross n matrix, n cross n Hermitian matrix. So later you will see that this assumption of Hermitian is not required, but for the time being, because this is how in the textbooks it is defined. So suppose that we have a Hermitian matrix of size n cross n. Okay, then A is called positive definite, and I may use this abbreviation for this P dot D dot. So A is called positive definite if x star AX is greater than 0 for all non-zero x in Cn. Okay, so if x star AX is greater than 0 for all vectors x in Cn, then A is called positive definite. And similarly, you can define positive semi-definite. So a matrix is called positive semi-definite. So the same way, if x star ax is greater than equal to 0 for all x in Cn. Okay, so let A be n cross n Hermitian. Same way, then A is called positive semi-definite. Or I may use this PSD, this abbreviation, if x star ax is greater than equal to 0 for all vectors x. So you don't have to mention now non-zero because it is greater than equal to 0 for all x in Cn. Okay. Now clearly you can see that if a matrix is positive semi-definite, so positive definite implies A is positive semi-definite. So if A is positive definite, then by definition A is also positive semi-definite. Right? It is clear from the definition. But can you say the converse is also true? So what is your answer here? At least by definition, you cannot say this in general that PSD need not imply PD, that means positive definite. And why it is? So you can construct any example at least. When you will see several properties of this definite and semi-definite matrices, then you will immediately give me as many examples as you want for this PD and PSD matrices. But for the time being, so far we only know the definitions. So let us take this that all entries are equal to 1. Okay. Now we want to check first that whether this A is PSD or not. So how to check that? So far we just know the definition. So we just need to see that what happens when I calculate this x star ax for any given x. Can I say that it is greater than equal to 0 always? So if I take, let's say, any vector x, let's say x1 x2 with components x1 x2 in C2, and if I compute x star ax, then what it is? So it would be x star is just x1 bar x2 bar, then A is 1 1, and then x is x1 x2, right? So what it would be? So it would be x1 bar plus x2 bar, and then x1 bar plus x2 bar, x1 x2. So what is this? This is just x1 x1 bar plus x1 x2 bar plus x1 bar x2 plus x2 x2 bar, right? So what we can say here that the first term is x1 square mod x1 square, the last term would be mod x2 square, so I will write this also, and then the middle two term, they are just conjugate of each other, so there would be twice of real part of x1 x2 bar, or you can say x1 bar x2, same thing. Now how can we show that this thing is greater than equal to 0? Any idea? So I want to show that this matrix is semi-definite. For this, I need to show that this x star ax is greater than equal to 0. So if I somehow show that this quantity here in the right hand side, this is always non-negative, then I'm done. I can say that A is semi-definite. Can we make it like this term as a? Can we do something, add or subtract, so that it becomes non-negative, or it is easy to see that the right hand side is non-negative?
So real of x1 dot x1 bar product x2 is smaller than mod of x1 into mod of x2.
Okay. So
Then
so you are saying that x1 bar x2, the real of this is less than mod of x1 mod of x2. I agree. But before that you want to, so you want to use that. How we can do that? So you are saying that you add and subtract like mod of x1 and x2. This is what you are saying. So let me know if I'm doing as you are thinking. So I will add twice of mod x1 and mod x2, and then I'll subtract and I will also add same thing here, and then this term 2 real of x1 bar x2. Right. Now the first three terms, they are just mod x1 minus mod x2 whole square. And the last two term that you can write as mod x1 x2 plus real of x1 bar x2. Now I can see what you were saying. You are saying that this term here is always greater than equal to 0 because mod of x1 mod of x2, this product is greater than real part of x1 bar x2. So this is true, and therefore this is greater than equal to 0. And this term is again anyway square of real number, so it is always greater than equal to 0 again. So what you can say from here, you can say that this implies that x star ax is greater than equal to 0. So this implies A as PSD. But can you say that A is positive definite from here? So we have seen that x star ax is always greater than equal to 0 for all x. But can we say that this is greater than 0 when x is non-zero? For this matrix A here?
No. No, sir.
No, why? If no, then you will have to give me a vector which is a
If
non-zero
we take, sir,
vector. So,
1
yes,
minus 1. If we take 1 minus
yeah,
1.
yes, I understand. So what you're saying. So he's saying that if you take x as 1, then this x is non-zero and x star ax is 0. So this implies that A is not positive definite. So definite matrix implies that A is positive semi-definite, but the converse is not true. In fact, as if you recall, I mentioned here that in the definition of positive definite matrix, this this condition is actually redundant. You don't require this assumption. This assumption here that x star ax is greater than 0. Greater than 0 means implicitly we are assuming that x star ax is real. Then only you can say x star ax is greater than or less than 0. The ordering is defined only in the real numbers. So we are assuming that x star ax is real. So seeing that x star ax is real for every x is equivalent to saying that A is Hermitian. So this assumption is actually redundant. So what I'm saying is the following. In the next result, you can see it. I'm saying that if you have a matrix A, let's say n cross n matrix, then A is Hermitian. A is Hermitian if and only if x star ax is real. So this quantity is real. X star ax is real for all x in Cn. So if you now you can see that if this result is true, then whatever I have assumed in the definition, that is redundant, because you can see that x star ax greater than 0 means I am assuming that x star ax is real for every x. But then because of that result, this implies that A should be Hermitian. So this condition itself implies that A is Hermitian. So this is a redundant assumption. We can actually drop it also. But in the textbooks, in all the textbooks, this assumption is made. So this is how it is defined. Especially, it is to mention when you have a real matrix, so real symmetric. So this is true when you have a when you have a complex matrix. So what I'm saying is that if you have a real matrix A, and if X transpose AX for all X, you know that X transpose AX, A is real, X is the real vector of size n, then X transpose AX is also real. But then this does not imply that A is symmetric. Okay. So this is true when this is when X is varying over Cn. So if you x star ax is real for all x, then only you can say that A is Hermitian. But if A is a real matrix and if you take any real vector, then x transpose X is always real. But then this does not imply that A transpose A. So just to differentiate this thing, they have assumed that A is Hermitian. But if you keep in mind that this thing is true, and there the vectors are taken over all Cn, over all vectors in Cn, then you actually don't have to assume that. Okay, I hope I made my point. So I'll remove this. Now, why this result is true? So why this result is true? So this is if and only if, again, we have to look at both the direction. So if A is Hermitian, then you can easily show that x star Ax is real. So how to do that? So let us suppose that A is, so let A be Hermitian, and X is a vector in Cn. Now I have to show that x star Ax is real. Can you show me how to, or can you tell me how to do that? So I have to show that x star Ax, this is just a scalar. X star Ax is just a scalar. I have to show that this scalar is a real number, using the fact that A is Hermitian. So how to show that a complex number is real? Just show that its conjugate is equal to the number itself. So if I show that the bar of this number, the conjugate of this number is the number itself, then you can say that x star Ax is real. Now, how to show that x star Ax is equal to its conjugate? Any idea?
So take its bar, then take the transpose.
Yes. So x star Ax is just a scalar. So conjugate means you can say that you just take the conjugate transpose. It's the same thing because it's a 1 cross 1. It's a scalar, so 1 cross 1 matrix. So it's the same thing. Now this you can write as x star A star X. But then you know that A is Hermitian, so A star is equal to A. So this is equal to x star Ax. So this implies that x star Ax is real. And we have started with an arbitrary x. So this is true for all x. Okay. So if direction is straightforward. Now let us look at the only. So what is given? The given is x star Ax is real for every vector x in Cn. Using this, we have to show that A is Hermitian. Okay. So A is Hermitian means, so if I assume that A is of this form, that means the entries of A are denoted by Aij, then I have to show that Aij, so what is our claim? Our claim is to show that A is equal to A star, or equivalently, Aij is equal to Aj bar. right? This is what I have to show for all ij, I and j. Now, how to do that? Now, here one observation is important. So x star ax is real for every x. Now you see here, if I take any two vectors x and y in Cn, and if I look at this x plus y star a x plus y, now what is this? This is x star ax plus x star ay plus y star ax plus y star ay. Now by the given assumption, x and y are vectors, so x plus y is also a vector, so the left hand side is a real number. This belongs to R, right? Because of the assumption. And also here this element is in R because x star ax, so for every x star ax is in R, so this is in R. Similarly, this is also in R by assumption. So what we can say from here, that left hand side is in R and these two terms are also in R, so this term is also in R. So what we can say from here, that this implies that x star ay plus y star ax is in R for all xy in Cn. Now this is interesting and this is also important for us because it says that for any two vectors x and y in Cn, x star ay plus y star ax is in R. Now if I choose particular vectors x and y, and then using them I can show that aij equal to aji bar. Okay. Now you look at this. If I choose x as ek, let's say, and y as ej. So you know what is ek and ej? They are the ek is the kth standard unit vector and ej is the jth standard unit vector. You can also write it instead of ki. So let's say ei. So let's say x is equal to ei and y is equal to ej. So then from this inequality, let's say from this equation star, so then from star what we can say, it would be ei star a ej plus ej star a ei in R. But can you tell me what is this ei star a ej?
aij.
So this is aij, just the ijth entry of A. And what about this one? This would be just aji similarly, right? So what we can say that aij plus aji is in R. Okay, fine. But from here we cannot say that aij is equal to aji bar. So what we can say is that aij plus aji is in R. So I have taken any I and j. So whatever I am saying for I and j, it will be true for all indices I and j. So let us focus on this. Right? So if aij plus aji in R, then what does it mean? It means that if this is in R, then the imaginary part of this is 0. Aij plus aji is 0. So let us give it 1. Similarly, I will show that the real part of something is 0, and using those two equations, I would be able to say that aij is equal to aji bar. Now what I will say, now again you let x as I ej. So now you see why I was using k here, because I want to use the complex number I. So just I'm replacing I by k just to avoid the confusion. I'm replacing I by k. Okay. So because I want to use I as the complex number. Now I'm in the next step, I'm taking x as IEK and y is just EJ. Okay, and I will do the same thing. So then what I get? So it would be IEKJ star AEJ plus EJ star A IEK. This is in R. But then what it is? The left hand side, it would be minus I AKJ, and the right hand and this side would be A I A J K. So what we can say from here, that I will write it again. So I can say that this implies minus I, so minus I AKJ plus I AJK is in R. But then this means that the real part of AKJ minus AJK is equal to 0. Let us call it 2. Question number 2. Okay. Now from 1 and 2, so from 1 and 2, what we have from 1 and 2, we have that for any indices k and j, real part of AKJ minus AJK equal to 0 and imaginary part of AKJ plus AJK equal to 0. Does this 2 implies that AKJ is equal to AJK bar? Can you see it? Just verify this. So what I'm saying that these two equation implies that AKJ is equal to AJK bar. But then this implies that A is equal to A star. A is Hermitian. So the only thing is to verify this thing. Now why this is? So you can easily verify, assume that W and Z are two complex numbers. So this AKJ and AJK are complex numbers, right? So assume that W and J are two complex numbers and imaginary part of W plus J is equal to 0 and real part of W minus J equal to 0. This will implies that W is equal to Z bar. So I'm just using that. So you can write W as W1 plus IW2, Z as Z1 plus IZ2 and just do the calculation. You will get this. And therefore we can say that A is Hermitian and this completes the proof. So if X star AX is real for every X in Cn, then we can say that the matrix is Hermitian. Okay, and we are done for the class. So if there is any doubt, you can ask. Otherwise, we'll stop here. Okay, so Soumya Shri, you have raised your hand. Do you have anything to ask?
Yes, sir.
Yeah.
Sir,
Just
yes.
1 minute. Just
Okay.
1 minute. So when I'm sharing my screen, I'm not able to see who is raising their hand. So please, whenever you have anything to ask, just speak out. Okay. Just stop me in between and then say what you have.
Okay, sir.
Yeah, please tell.
Sir, on February 8th, we have our minor exam of one of our other subjects. So
Minor
that is from
exam
5.
starting. Yeah, my minor exam starts from 14th.
Yes, sir, but the professor of that subject decided to take 2 minor exam before one before the institute minor exam time and one after that.
But then when did he announce? Because I announced earlier. I mean, already I had announced about this quiz. I had announced about this quiz, I think last week, right?
Yes, sir.
So when did he announce this? So did you oppose there also?
Yes, sir. Actually, I am not aware about the quiz time, so I just only said him कि there will be a quiz on Tuesday, but he said कि what time it will be, but I said
So what
maybe
time your exam is?
5
on
to
Tuesday?
7 p.m.
5 to 7. And we are planning from 6 o'clock.
Yes, sir. If it will be from
Alright.
4, then it will be okay.
But then 4 other students have issues.
So maybe we can have at 7:30.
So we can have it 7:30. Is it okay, Someshri?
Yes, sir.
7:30? Would it be fine for you giving 2 exams in a day? I mean, I don't want to give extra burden, but the only thing is that I want to have a quiz before minor. And you know that immediately after that week, we will have a minor exam. So I don't want to postpone it also. So either we prepone it, let's say on Monday, if you want, we can do it on Monday. Or let's say Wednesday sometime, if you suggest.
Yes, sir, that will be better. I have also the exam on Tuesday, so.
Okay. So how about others? Can we do it on Monday or Wednesday? Wednesday 6 o'clock or 6:30 or Monday 6:30 after the exam, after the class here. That also we can do.
Sir, Wednesday.
After 5 o'clock on Monday, anytime.
Sir,
Yes, Dave.
Monday I have a class.
You
So
have a
Wednesday
class till
6:30 को एक बच्चे
6
को प्रॉब्लम
to
थी सर.
9.
6 to 9.
Yes, sir.
Okay, okay. Yes, Dave, you were suggesting something.
सर Wednesday 6:30 को सागर को प्रॉब्लम थी सर in the last class he said.
Acha, Sagar is not here now.
So we
Oh
can
yes, so he is
have
traveling. He said he is traveling.
yes,
Okay.
afternoon में if possible we can have.
Sir, Wednesday before 6:30, like 4 or 5 p.m.
No, but there were some students who were having some problem on Wednesday.
Sir, Wednesday afternoon I think there is no problem to anyone.
Wednesday afternoon is fine. Wednesday 3 p.m. But there, I remember there was one student who was having some problem for Wednesday. He
Sir,
was
I
traveling
said
or
that
something.
I have class, but the class will be over before 12.
So what time is you are free? I mean, everybody is free on Wednesday. 3 p.m. is okay.
Sir, before 2, he said, I think Sagar.
Before 2 is fine, huh? So you have to suggest me some timing on Wednesday. After 2 p.m., that means the 3 p.m. we can we start on 3 p.m. on Wednesday? Or you want me to have it on Sunday so that everybody is free? There is no class, there is no issue. Just for half an hour.
But
Is it
sir,
okay? Yes, going.
Sir, we have gate exam on Sun. No,
Oh
sir,
yes,
it's fine.
you have got exam. Yeah. Gate exam is on Saturday, right?
But sir, we have traveling, so in the last
अच्छा
day.
अच्छा 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 ठीक है. Okay. Okay, so then Wednesday 3 p.m. I will propose, and then let's see what happens.
Sir, he's saying before 12.
Before 12. So how about others? So others might be having some class before 12 then. Okay, so what time then? If you want me to have before 12, then what time? Oh, okay.
No, sir, before
let's
12
see.
is not fine for.
Before
At
12 is?
3, it is okay, sir. At 3 p.m., it is okay, sir.
At 3 p.m. is okay for you, but like others, somebody else was having some problem. So then Wednesday is like you are not converging at at a common time. So then what can we do? Can we have it on like Monday? So can you suggest me some time on Monday? Let's say late evening. Let's say 7 o'clock or 7:30.
Sir, not
Monday.
on Monday. Sir, actually, I'm traveling on Monday, so it's not
So you're
possible.
traveling and
for me.
somebody has some other class on Monday also.
Yes, sir.
6 to 9.
Yes, sir.
Okay, 6 to 9. Okay. Okay. Then Tuesday late evening. Is it okay? Tuesday 7:30 because
Yes, sir.
Tuesday.
Sir, he convinced for 2 to 3.
no 2 to 3 is fine, but they are having like somebody
So
else was saying
Wednesday 2
minus.
to 3.
Wednesday 2 to 3, but you said Sagar said before 12.
No, sir, I am talking to Sagar. He said 2 to 3 is fine.
2 to 3 is fine. Okay, Dev. Thank you. Then okay, so is there anybody else who is having problem from 2 to 3 on Wednesday? If not, then please you try to manage, because otherwise we won't be able to converge at one time. So let's, for the time being, you assume that it would be from 2 to 3 on Wednesday. If I get any message or any email from your side, I mean from those who are not here in this class at this point, they might be having some issue, and if this comes, then we will have it at 7:30 on Tuesday. All right, so these are the two options. So first preference is 2 to 3 on Wednesday. If there is some, there are some cases where students are not available in that during this window, then we will have it on 7:30. It would be just half an hour exam, or maybe 45 minutes. So it should not be a problem. So then we will have it Tuesday at 7:30. All right. I hope that everybody is fine with this. Okay, so then we can call it for the day. Thank you, and I'll see you in the next class.